Squared hinge laws. In the last lecture, we learned about hinge laws. What is hinge laws? It is a loss function which is used for binary classification. We also learned that the speciality of hinge laws is that it classifies with a particular confidence margin. We had defined a confidence margin and it would simply not say it is class 1, class 2, but it would say with confidence because of the confidence margin. This time, when we are coming to squared hinge laws, there has to be some additional advantage that is provided by squaring. Then only you will be using squared hinge laws. So, let us understand what are those additional advantages that squared hinge laws will bring in. First of all, keep in mind whatever we learned in the last lecture, that in the hinge laws, we had a hinge at y into f of x equal to 1. That is why it was called as hinge laws. And we also understood that if it is purely correct classification and you are beyond the margin, then you would say loss is equal to 0. If it is not confident enough, but still even if it is correct classification, you would give a loss. If it is wrong classification, anyway, there will be loss. Coming to squared hinge laws, let us see how these things are changing. Okay. So the first thing, like we did in the last lecture, I'll just introduce the terminology. X is the input that we are having. Whatever is the input, we are calling it as X. What is Y? Y will be element of minus 1, 1. That means it can take only two values, minus 1 and 1. And this is the true label. That is the actual class this input X is belonging to. That is what we are calling as Y. Next thing is f of x. I'm using the same notation as we used in the last lecture so that it stays relatable. F of x is the model output. So once you feed x into the model, whatever model produces, this is called as f of x. This f of x, it is not probability, it is a score. The same situation as we explained in last lecture. Next thing is, what exactly is the loss function in squared hinge laws? In case of hinge laws, in the last lecture, we had seen loss function was something like this. Loss of y and f of x. This we had written as maximum of 0 and 1 minus y into f of x. This is what we learned in the last lecture. I'm not explaining this now because we also already went through in the last lecture. Here you can note that there is no loss. Loss is equal to 0 if y into f of x is greater than or equal to 1. This is the scenario we had. Coming to squared hinge laws, loss squared hinge. In this case, the difference is going to be y into f of x. This will be maximum of 0, 1 minus y into f of x. This will stay as it is, and then you'll square this term. At this point, you may think it is simply a square added and there is not much difference this is going to bring. This is where we are having this lecture. What all are the differences simple squaring is going to introduce? This is what this lecture is going to discuss. Okay. So the first thing, let us understand different cases, what happens there. Then we'll see what are the specific advantages that squaring is going to bring in. Okay. First, we'll clarify basic steps so that everyone are on the same page. First thing, what are the possibilities here? Y is the label, which means it can take minus 1 or 1. So f of x is your score and y into f of x, it can be either positive or negative. There are two possibilities. Whenever it is positive, you are saying it is right classification. Whenever it is negative, it is wrong classification. How does it work? Whenever true label is minus 1, f of x should also be a negative number. Then minus 1 into negative number will be a positive term. That is when y into f of x is greater than 0, then you will say classification is correct. I am saying just classification is correct. Still you may assign loss, but your classification is correct. Next thing, if class is 1, then 1 into any positive term will give a positive value, which means if your y into f of x is positive, if this is greater than 0, that case it will be correct classification. So depending on whether -1 or 1 is whichever is the actual right class, accordingly value of f of x outputted by the model, I told you it is a score and it is not a probability. That score, if it is positive, you will say it is right. If it is positive for class 1, or if it is -1 class, then it should be negative. In total, you can understand, if y into f of x, if this term is positive, your classification is right. If this term is negative, your classification is wrong. Whatever classification model has done is wrong. Now, we know this is the loss function. Another way of writing the same loss function can be, okay, I'll just write it down here. I'm writing both ways because for analysis we'll take the other one. Okay, so the same thing, this can also be written as, another way of writing the same thing is 0 is the loss if y into f of x, if y into f of x is greater than or equal to 1, and 1 minus y into f of x the whole square, this is the loss if y into f of x is less than 1. This is another way of writing the same thing. Okay, both are one and the same. Here I split it into two parts. Here I put inside the max. Both will give you the same result. Now let us see what happens to loss in each case. First case is, what if y into f of x, what if this value is greater than or equal to 1? If this is greater than 0, then itself your classification is correct. So anyway, if it is greater than or equal to 1, your classification is surely correct. Your prediction is right. Plus, you will say you are already beyond the margin, so your loss is equal to 0. Next case is, what if this is a value between 0 and 1? So 0 less than y into f of x, y into f of x less than 1. That is, value of y into f of x is between 0 and 1. So we know if it is greater than 0, classification is right. So here also your classification is right. But the same way we used loss in Hinge loss, here also you have quadratic penalty. Quadratic penalty. So another way is, loss is 1 minus y into f of x the whole square. This will be the value of your loss. And the important point here is, this loss value, this will be between 0 and 1. Still, it is almost the same as previous Hinge loss. It is going to change from here on. Okay, the characteristics are going to change. Next thing, the third case we are going to take, what if y into f of x is less than 0? Here it was between 0 and 1. What if it is less than 0? This case, classification is wrong because y into f of x is less than 0. Classification is wrong, which means you have to give quadratic penalty again. 1 minus y into f of x the whole square. This is the penalty you are giving, and loss will be greater than 1 here. Loss will be greater than 1. At this point, till this point, do you feel like it is quite similar to Hinge loss? Whatever you learned in Hinge loss, almost the same things we learned here. But now let us analyze and see what are the difference inside whatever we have already written. Okay. If you see this, I'm going to explain what is the speciality of squaring. Okay. So coming to the specialities of squaring, first thing is, when we learned about Hinge loss, in the last lecture, when we learned about Hinge loss, we saw that at the point y into f of x equal to 1, it was not smooth at all. The first differential, it was even one time it was not differentiable. First derivative itself did not exist. It was not differentiable at y into f of x equal to 1. This is what we had seen because it had a hinge-like shape, and at this point it was not differentiable. Coming to squaring, what squaring does is, it smoothens up this shape. Because it smoothens up, it the first derivative this time is available. It is smooth and it is continuous. So this time you are not having that hinge. Even though we are calling it as squared hinge loss, this time we don't have that hinge like the previous case. This time it is smoother. So because of squaring, the advantage that you got is this time first derivative. I'll write the advantages here. Advantages of squaring. Okay. First advantage is it got smoothened up. That is differentiable everywhere. It is differentiable everywhere. Differentiable everywhere. This is the first advantage. Coming to loss functions, staying differentiable is a big advantage because let us say you are using gradient descent or anything, you always want to take the gradient and then work on it. So given that even at this point it is differentiable everywhere, it smoothened up your whole graph. This is the first advantage that you got by squaring. Second advantage, it is hiding here. Try to understand the second advantage. It is hiding somewhere over here. You will feel like the formula is almost similar to hinge loss, but there is a big advantage. The second advantage is, in case of previous hinge loss, the standard hinge loss, what we had seen is if the margin is greater than 1, then you are saying loss is equal to 0. If margin is less than 1, greater than or equal to 1, you were saying loss is 0. But when I say margin, it is y into f of x. This particular term is what I am referring to as margin. Okay. So if the margin is lesser than 1, there is a case where if it is between 0 and 1, I am writing m as margin for y into f of x. Okay. If this margin is between 0 and 1, we are giving a linear penalty, and the same linear penalty was given if m is greater than 1. If margin is less than 1, even if less than 0. That is wrong. What I mean to say is, here classification is right, just that your margin is wrong. You are giving linear penalty. Here classification itself is wrong. It is saying the identified class itself is wrong. Still, you are giving the same linear penalty. Obviously, the value would linearly increase according to the error here. But still, the penalty is linear in both cases. Here also it is linear. Here also it is linear. Now, when you look at this equation, maybe you will tell me, here it is quadratic, but again it's the same case because here also it is quadratic, here also it is quadratic. But there is a small catch here. What is the catch? The catch is that even though both these are quadratic, the effect that this quadratic brings in is different in both cases. If you take this case, here your margin is very less. What happened here? Your y into f of x is less than 0. So when it goes lesser than 0, what happens in this particular scenario? Your loss will be greater than 1. If your loss is greater than 1, here the loss is greater than 1. Loss is greater than 1, then you are squaring this loss. You are squaring a term which is greater than 1, then the value of that term will increase very highly. For example, if you take 2 is your loss, if you square it, it becomes 4. If 3 is your loss, you square it, it becomes 9. If 5 is your loss, you square it, it becomes 25. So whatever is your actual loss, that is being magnified when you are squaring. But what happens in this case when loss is between 0 and 1? When loss is between 0 and 1, this is loss greater than 1. If loss is between 0 and 1, in this case, actually squaring is going to diminish the effect of your loss. Let us say your actual loss is 0.9. So 0.9 is the loss. When you square it, what happens? It becomes 0.9 into 0.9 will be 0.81. So this is a smaller value than 0.9. What happened? When you squared it, the actual value, the magnitude of the value actually decreased. Here in case loss is greater than 1, that is wrong classification. Here the value is increasing, but in right classification, but margin is not good enough, then the value is decreasing. If I put, let us say 0.5, it will be 0.5 into 0.5 will be 0.2 0.25, so which is a smaller value than 0.5, and you can see it is decreasing. So even though both these are squaring, the effect that it is building is different depending on whether it is right classification case or wrong classification case. In wrong classification case, it is magnifying. In right classification case, it is diminishing the loss. So this is the second advantage you are getting when you are using squared hinge loss, right? So the first advantage, it is staying differentiable everywhere. First derivative is available everywhere. I am again stressing on first derivative because second derivative is not. So I'll show this. I'll show it mathematically, then you will understand. Second thing is the effect it is bringing in case of right classification and wrong classification. Here it is clearly able to say this is right wrong classification and I am giving a greater loss. Here it is right classification, so I am still penalizing, but I am giving a smaller loss, right? So this is the scenario. Next thing is, let us see how to take gradient. We'll see how to take gradient. Then we'll also understand how different derivative exist, not exist, and all those cases, right? So first, next thing I'm going to do is I'll first remove these things off. Let me erase these. Let us take the gradient now. So whenever you are using a loss function, you should know how to take gradient. Gradient is a very important part. So let us understand gradient. My loss function, okay, I'll keep the same form itself, y into f of x the whole square. If I take gradient of this, what happens? I want to take gradient with respect to f of x. If I take del L by del f of x, this is the gradient. What happens in both these cases? I'm going to take gradient of both these. First one is easy, it is 0, so it will be 0 itself if y into f of x is greater than or equal to 1. Then it will be 0 only. It is very simple. Second one, 1 minus y into f of x the whole square. If I take gradient, what happens? First, this 2 will come to the other side. So it will be 2 into, okay, I'll show you how to take it. If I take derivative of d by df of x of 1 minus y into f of x the whole square. If I do it, what happens? This will be 2 times 1 minus y into f of x, 1 minus y into f of x into d by df of x of this term, right? So whatever is inside, 1 minus y into f of x. So then when you take this d by df of x, what happens? Here minus y will be remaining. So here I can write minus y. So if I write this forward, it will be minus 2y into this term. So here I can write minus 2y into 1 minus y into f of x. This will be the case if y into f of x is lesser than 1. So greater than or equal to 1, this is the scenario. Lesser than 1, this is the scenario. Now I'll show you how is the gradient smooth. If I show this thing, let us see why it is smooth. For it to be smooth, the requirement is we are only considering this point. We already know that y into f of x equal to 1 is the point where it was not smooth in the last lecture. So if you remember from the last lecture, we had seen that for hinge loss, at the point y into f of x equal to 1, it was not smooth. Here I am saying it is smooth. So I am going to prove it mathematically, or first I'll show you graphically. Then we'll prove mathematically. That's better. So first I'll just draw the graph and show you. If you draw the graph, it will look something like this. The graph of y into f of x. If this is my situation, 0 here, 1 here, 2 here, 3 here. So on x-axis, I have y into f of x. Same case as the last lecture. On y-axis, I have loss. I am going to first draw the old one, that is standard hinge loss. What happens in case of standard hinge loss? So the loss will come like this. It will meet 1. After 1, it is having a hinge here. And after that hinge, it will go straight. Loss is 0 everywhere. So this is the scenario in case of standard hinge loss. I want to show you what is the change in scenario when instead of standard hinge loss, I am using squared hinge loss. When I use squared hinge loss, what happens? It is a squared part, so this part will be smooth. Instead of this linear line, it will come something like this. It will be coming something like this, and then, okay, let me draw again, because something like this, and then it will join here. So after this point, it is anyway 0, but it is smooth here, not like the previous one. In the previous case, you had a hinge here, but in case of the blue line is squared. Let me write it here. This is squared hinge loss, and the red line, this is standard hinge loss. So here I'll simply write hinge loss. Hinge loss we already saw in the last lecture. I want to show you how squared hinge loss is different. Squared hinge loss is this one, the blue line. You can see the blue line is smoother. But in the case of red line, which is for hinge loss, you had a hinge here. Let us now see mathematically how is that hinge disappearing. First, I'll write just the loss function. Loss function, I'm writing m because this y into f of x, I don't want to repeat it again and again. So I'll simply write this is 0 if m is greater than or equal to 1, and it is 1 minus m the whole square if it is lesser than 1. So this is the scenario. What happens if I take the derivative? This is what I want to see. If I take the derivative L dash of m, the 0 will remain as it is. 0 if m is greater than or equal to 1. The other case, this is important. 1 minus m the whole square. If I take the derivative, it will be 2 into 1 minus m into derivative of 1 minus m. So that will be minus 1 because it is minus m. So derivative will be minus 1. Instead of multiplying minus 1, I am putting a minus here. So minus 2 into 1 minus m. This is the derivative if the value of m is lesser than 1. This is my derivative. Why am I saying that at m equal to 1? Okay, so this should be when it is greater than 1. This should be when it is less than 1. Next question is, what happens when m is equal to 1? At m is equal to 1, what is the story? This is what we are interested in. At m equal to 1, if the derivative has to exist, what should happen? The left derivative and the right derivative, both of these should be the same. Then only you can say derivative exists, it is differentiable. So let us see what is the left derivative, what is the right derivative, and are they equal? This is what we want to see. If you take the left derivative can be L dash of 1 minus. This minus shows it is left derivative, okay? How will you take left derivative? On the left side of 1, this particular formula holds minus 2 into 1 minus m. So if I use that minus 2 into 1 minus, what is the value of m here? We are checking at m equal to 1, okay? At m equal to 1, we are checking m equal to 1. So 1 minus 1, that is minus 2 into 0, this will be 0. What about the right derivative? If I take right derivative, this plus shows it is right derivative, okay? Equal to, on the right side of 1, this formula holds. So it is 0. This is why left derivative also 0 here, right derivative is also 0 here. Which means both left derivative and right derivative are the same. The value is staying the same. If you move slightly towards the left, then also it is 0. If you move slightly towards the right, then also it is 0, which means it is smooth. See, if it is not smooth, only if you have a point, then you move slightly towards the left, you get a different value. You move slightly towards the right, you get a different value. Then you say it is not smooth. But if both sides you have the same value, that means it is smooth at this point, right? This is the logic. If it is same at both sides, that means it is smooth at that point. We are only considering whether it is smooth at m equal to 1. Okay, only this point we are checking. One thing I'll do, I'll just show you why it is not smooth in case of standard hinge loss. Then it will be more clear for you. What we'll do is, we'll take standard hinge loss and I'll just show you why it is not smooth in case of standard hinge loss. Okay. In case of standard hinge loss, what did we have as the formula? we had loss L of m. Instead of that squaring, it was something like this: 0 if m is greater than or equal to 1, and 1 minus m if m is less than 1. This was the scenario in case of standard hinge loss, not squared hinge loss, standard hinge loss. I'm showing you why it was not differentiable there, okay? If you take the derivative L dash of m, what happens now? 0 will remain as 0 if m is greater than or equal to 1. What happens to 1 minus m? It will become minus 1 because minus m's derivative is minus 1, right? So minus 1 if m is less than 1. This is the case in case of standard hinge loss. If this is the scenario, then if I take the left derivative, L dash of 1 minus the left derivative, how will you write it? Limit m tends to 1 minus dl by dm. This is what you call as the left derivative. Here what is the scenario? On the left side you have value minus 1. Minus 1 is the value. What about the right side? The right derivative L dash of 1 plus, if you take right side, this one holds. Here again it should be greater than 1. This one holds. So the value is 0. Here if you see, left derivative is minus 1. Right derivative is 0. So if you stay at m is equal to 1, if this is the point, left derivative is a different value, right derivative is a different value, which means it is not smooth at this point. That is why in case of normal hinge loss, standard hinge loss, this is the standard hinge loss stuff. In this case, it is not differentiable at m is equal to 1. But when it is squared hinge loss, here you have same value for left derivative and right derivative. It is differentiable at m is equal to 1. This is why it is smooth. Graphically, if you see the normal hinge loss, the red line, it is not smooth at m is equal to 1. At 1 there is a hinge. But in case of squared hinge loss, the blue line, you can see it is a smooth curve and hence it is smooth at m is equal to 1. One more thing, I told you second derivative is not there. So if you want to see that as well, let us see. Let it be clarified. So if you take the second derivative, what happens for this same thing? This is the first derivative. If you go for the second derivative, then it is not. If you see L double dash of m, if you go for the second derivative, it will remain as 0 if m is greater than 1, but it will be minus 2 into 1 minus m. This when you take derivative, what happens? Minus 2 into 1 minus m's derivative will be minus 1 because minus m's derivative will be minus 1. Minus 2 into minus 1 will be plus 2. So I'll write 2 here. 2 if m is less than 1. So here you can see on the right side you have value 0, left side you have value 2, which means left and right derivatives are not same. Second derivative I'm talking about. So second derivative does not exist for squared hinge loss. So first derivative is continuous, it is smooth, but second derivative is not. That means it is once differentiable, but it is not twice differentiable, okay? So first derivative exists, so you can say it is a smooth curve. So smoothness increased when you changed from hinge loss to squared hinge loss, but still the second derivative or the higher ones doesn't exist. First derivative does exist, it is smooth. What else is remaining in this lecture? I think we are done with squared hinge loss. Okay, so in this lecture you learned what is the advantage that you got by squaring standard hinge loss. Whatever was the hinge loss you had, you simply squared it. By squaring you got certain advantages. That is what we discussed in this lecture for squared hinge loss, right?